Alright gang, here we go. This is for Chem 1, Unit 9, Part 5. We're talking about solids, phase changes, phase diagrams. Should be a lot of fun. Hopefully, you've realized by now that we can kind of, whenever we're thinking about these different states of matter, that we can just kind of think about the liquids, the matter that we're talking about as different point particles. And the closer they are together, the more they have either solid, liquid, or gaseous quantities. You know, gases being the very, very farthest apart, solids being really, really close together, and liquids somewhere in the middle, closer to solids than gases, because, but whatever. So solids, essentially the same idea as what we've been talking about for liquids, but instead of them being able to flow past each other like in a liquid, they're stuck, and they have a definite crystalline shape, and because of that, they have a definite volume. All right, and so one of the defining characteristics of solids is they have to have a definite melting point, which is super interesting, that you can actually see, and hopefully we'll get to see this in classes. You'll get to see that when you hit a specific temperature, the thing you have starts melting right there. Right below it, it doesn't melt at all. Okay, and so obviously solids have high density. Okay, because these molecules are very, very close to one another, and they're also incompressible. Okay, if you increase the pressure, it doesn't change the volume of that solid. Okay, phase changes, so you just need to know these. Most of these should be pretty simple. Solid to liquid, this is freezing. Okay, liquid to solid. Oh my goodness, that's embarrassing. This is what I get for answering the one after instead of the one I'm on. Solid to liquid is melting. Very good, very good. All right, and then freezing. All right. Solid to gas, this is sublimation. All right. Gas to solid is called deposition. All right, this is the one most people can't quite remember mostly. Gas to liquid is vaporization. No, condensation. And then liquid to gas is vaporization. Now, one thing that you need to keep track of is that all of these different phase changes are not chemical reactions. They are physical reactions, or physical changes. So really what this means, remember, in a chemical reaction, we're breaking or forming those chemical bonds. In a physical change, we're messing with the intermolecular forces. Okay, with intermolecular forces. So when you go from a solid to a liquid, you're overcoming intermolecular forces, but your compound is still exactly the same as it was. All right, you're not breaking or forming new chemical bonds. All right. Last thing about phase changes before we jump into fun stuff here is the difference between an endo versus an exothermic change. All right, you probably learned these terms before. All right, but endothermic is when heat is absorbed in order for the change to occur. All right, and so really we're going to talk about endothermic versus exothermic in lots of different cases. Today we're just introducing them with physical changes, but they can also occur with chemical changes as well. All right, so with an endothermic reaction, your thing is absorbing heat. Heat is entering into your whatever it is. Okay, so if you're melting ice, you have to add heat in order for it to occur, right? If you want that ice to melt, you got to put heat in. All right, so that is a endothermic process because you got to put heat in. Exothermic is when heat is released as the change occurs. Okay, if you want to freeze ice, right? So in your ice maker and your freezer at home, you've got your water. It comes in and it gets squirts into the ice tray, and then your heat pump pumps out the energy from your freezer and reduces the energy of that water. So energy is leaving your water in order for it to freeze. Okay, and so that's called exothermic. All right, so exothermic is when heat is released as the change occurs. All right, so here's a heating curve, and we just looked at this in the previous video. Remember here, so let's just generally say that, so this is a solid. Remember, this is solid because it's at the lowest temperature, and then so therefore this guy would be our liquid, okay? And then this guy up here would be our gas, okay? And then so we have to think about these phase changes as they occur. If we're going from solid to liquid, well, if we go from solid to liquid, let's see, let's draw an arrow this way versus this way. All right, if we go from solid to liquid, we are melting, all right? And if we go from liquid to solid, we are freezing, all right? Freeze. All right, and if we go from liquid to gas, we are vaporizing. And then if we go from gas to liquid, we are condensing. Notice that we don't have sublimation or deposition on this heating curve, and mostly because it's pretty rare for it to curve, or for it to occur. All right, so we don't really focus on it with those heating curves. All right. So let's talk about this. So if we should be able to tell what's going on as far as endothermic or exothermic just based on this heating curve. So if we go from solid to liquid, that means we're melting, and because we're moving to the right here, we know that we're adding heat to our system. Okay, let's cross out this. This would be heat here. All right. Let's do heat because now it's a heating curve instead of time. So as we're going to the right, we're heating. Okay, so this means this would be an endothermic process. Endothermic. Okay. And then so would this guy here. In order to vaporize, we have to add heat in, so this would be endothermic. All right. And then to go from the right to the left, we're taking heat away. Okay, so that means this guy would be exothermic. All right, and then same thing here, condensation would be exothermic. All right, so you need to be able to identify which phase changes are endothermic, which are exothermic. All right, and be able to pick them out on a curve, a heating curve like this. All right, next thing here, phase diagrams. Now these are super interesting. Phase diagrams allow us to show or see the relationship between solid, liquid, and vapor in a sealed container. Okay. And it gives the pressure. We always have pressure in the y-axis, temperature in the x-axis. So we'll say y and x here for those three states of matter. All right. And then the conditions where two phases exist in equilibrium are indicated by a line that separate the two phases. So remember equilibrium, we talked about this when we talked about vapor pressure. It's probably been a while, so let's refresh. So equilibrium is when the rates of the changes are equal. Okay, when the rates of the changes are equal. All right, so that means if you got some sealed container, remember we reached vapor pressure, a dynamic equilibrium, when the solid, or the liquid, excuse me, was evaporating and formed enough gas that the gas was condensing just as fast as it was evaporating. And so you reach this point where the amounts of the two don't change. Now, that doesn't mean they're not equal to one another. It just means that the amounts of the liquid and the gas are not are not changing over time. You've reached this equilibrium point. All right. So it also shows two other points that are super interesting. We've got the triple point, all right, and this describes the only conditions where all three phases can exist in equilibrium with one another. So we have solid, liquid, and gas all in equilibrium with one another. Watch this video here. They do a really good job of developing. They show the freezing point of water. Or sorry, the triple point of water. It's really good. And then critical point is the position where you can no longer tell the difference between a liquid and a gas. All right, so that your gas starts to have some properties of liquid, but you can no longer compress it, but it takes up its whole container. And then, or you could look at it vice versa. It's a liquid that has properties of a gas, meaning that it doesn't have a defined volume anymore. It takes up the whole container. So anyway, but this video here is pretty awesome. It shows a substance reaching its critical point. They add a bunch of temperature or heat in order to reach the critical point. All right, so you need to know the definition of these two things and where to find them on a phase diagram. All right, so here's the generic phase diagram. We've got pressure in the y-axis, temperature in the x-axis. All right, it's always set up like this. We have solid here, and then liquid, and then gas. Solid, liquid, gas. All right, solid here, and then liquid, and then gas. Okay, now these solid lines here, separating solid to liquid, this is where we would have equilibrium between the solid and the gas, or sublimation and deposition phase changes. When we're here from the liquid to the gas, we have equilibrium between vaporization and condensation, and then when we're here on this line, we have equilibrium between melting and freezing. So the only places where equilibrium is achieved is when we're right on these lines. Now, don't let this confuse you. We exist in a place where you can think, to yourself that in the room you're in right now, if you have a glass of water, there's liquid water, but you could also have ice in it. And so you had a glass of ice water, but then some of it might have evaporated and there's going to be water vapor in your air. So if you find a pressure and temperature value in this thing here, just because you're in the middle of one doesn't mean you can't have the other phases. It just means that they're not in equilibrium with one another. All right. So the rates of melting versus freezing in your cup, the rate of melting is going to be much, much faster than the rate of freezing, but that doesn't mean it doesn't happen, all right, or it can't exist. And then we also have, so this is the triple point. Notice this is the spot where all three phases hit each other, and then we also have the critical point, which is up here. And so notice that here we no longer have equilibrium, and really what happens is we have like kind of a point here where this would be the critical temperature down here. Okay, this is the temperature at the critical point, and then this would be right here would be the critical pressure. All right, and so these 2 points here correlate with the temperature at which you reach your critical thing, and so anything that exists up here is called a supercritical fluid. Supercritical fluid. All right, super interesting stuff. Now water, now let's look at this. So this is like the typical phase diagram. Water is special because of all the intermolecular forces it can form. It's super weird, okay? Notice that this line between solid and liquid here, instead of it curving, oops, wrong way, this curve here has a positive slope to it, but with water, it's got a negative slope. So essentially what this shows you is that as you increase the pressure, your freezing point is actually going to change, okay? And this is shown by how the water expands as it freezes, okay, right? We know this, that water takes up more space. That's why we have to make sure our pipes don't freeze in the winter, okay? So here, at 1 atmosphere pressure, our freezing point is 0 degrees Celsius, okay? But up here, we notice that as we increase the pressure, our freezing point actually drops. Okay, and we have to get colder and colder at higher pressures. And so this is anything that has a shape like this or a negative slope between the solid and liquid lines is going to have that property where it expands as it freezes. All right. Also notice that water has because of the intermolecular forces, its critical point is at stupid high, 218 atmospheres, 374 degrees Celsius. That's 218 times the atmospheric pressure of the Earth. All right. They've got the normal melting point, this is the normal boiling point. All right, so notice at 100 degrees Celsius, this would be the normal boiling point. We're at 1 atmosphere. We talked about that in the previous video. And then this would be the triple point right here. Is at 0.01 degrees Celsius and 0.00603 atmospheres is where the triple point happens. Okay, yeah. Now, carbon dioxide is also super interesting, and we know that carbon dioxide is just solid carbon dioxide we call dry ice, right? And we've all played with dry ice, and you see that if you have a block of dry ice, it's going to sit there as a solid, but it's going to start sublimating right away. It's like the quintessential example of something that sublimates, okay? And the reason it goes straight from solid to liquid is because of this we can see the reason it does that based off the phase diagram. The phase diagram isn't the reason it does it, but we can see the properties of it that allow it to occur. Notice that the triple point occurs at 5.11 atmospheres. So you actually cannot form liquid carbon dioxide at all, okay, unless you're above 5 atmospheres. All right, so you have to increase the pressure. Otherwise, you can't form liquid carbon dioxide at all. At 1 atmosphere is way down here. If we have it as solid, okay, it's somewhere over here. We have to get it to like -78 at least degrees Celsius if we're at 1 atmosphere, and then as soon as we put it in room temperature, we might be up here. Okay, who knows? We don't really have a scale. We can't tell. But if we're up here, this is at room temperature and room pressure. Okay, obviously, since we're over here, the rate of sublimation versus the rate of deposition, the rate of sublimation is going to be much, much higher than the rate of deposition. And so we start forming that gas immediately. Okay, so this is really why carbon dioxide, this shows us that carbon dioxide cannot be a liquid. And so this is why it sublimates. Okay. And that's it for this part. All right, let me know, do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.